Consider a simple pendulum contains a bob of mass m attached to thread with length L. The bob moves along path x. The path x is an arc length which is equal to L theta. The kinetic energy is given as T equals m by 2 x dot square, but x from figure is L theta. So kinetic energy is m by 2 L theta dot square. Change in length with time is 0. So there is no theta dot term in kinetic energy. Potential energy, as we know, is mg, change in height during motion. From figure we can calculate that height changes from point A to point B. The change in height is just AC, which on simplification we can find is mgl into 1 minus cos theta. This term is potential energy. The Lagrangian is given as T minus V. The Lagrangian equation of motion contains terms such that partial L over partial theta dot and partial L over partial theta dot after time derivatives gives this one ml square theta double dot, and the partial derivative of n with respect to theta is minus mgl sine theta. So putting values of this term and this term into Lagrangian equation of motion, in this term we get ml square theta double dot plus mgl sine theta equals source term q. In first case, we apply small angle approximation such that sine theta is equal to theta and source term q is 0. This gives theta double dot plus g over L into theta equals 0. Theta double dot plus omega naught square theta equals 0. This is equation of harmonic oscillator. The simple pendulum behaves as harmonic oscillator. In this case, we can calculate time period and frequency of simple pendulum or harmonic oscillator using these g over L values. In case 2, we consider the source term is tau external, which is tau naught cos omega t. Here we also consider small angle approximation. So theta double dot plus g over L into theta equal tau naught over ml square cos omega t. Let us propose a solution, steady state solution. Theta of t is a cos omega t minus phi. Taking double time derivative gives minus a omega square cos of omega t minus phi. Putting values of theta and theta double dot back into this equation, we get terms containing omega naught square and omega square. A is amplitude of motion, so amplitude is given from this equation, tau naught over ml square over omega square minus omega naught square minus omega square. In case 2, we propose theta a cos omega t minus phi. On simplification, we get minus a omega square terms containing cos omega t, cos phi, sin omega t, sin phi. We expand cos omega t minus phi using this formula, and on simplification, we are left with cos omega t and sin omega t terms. Comparing both sides, we get a as alpha naught over cos phi into omega naught square minus omega square. So comparing coefficients of sin omega t on both sides of this equation, we get sin phi into omega naught square minus omega square equals 0. This term does not equal 0 because the simple pendulum or harmonic oscillator is in motion, so these terms cannot be 0. This implies sin phi must be 0, giving value 0 and phi. So at these two values, cos phi is plus minus 1. The magnitude of amplitudes from this equation we can get is alpha naught over omega naught square minus omega square. So putting value of this amplitude into proposed solution A cos omega t, we get for case 2 the theta t is alpha naught over omega naught square minus omega square into cos omega t minus phi. Putting back values of alpha naught, we get tau naught over ml square into omega naught square minus omega square into cos omega t minus phi. In case 3, we consider source term as minus b theta dot plus tau naught cos omega t. This is damping term and this is force driven term. So putting values of these, we get theta double dot plus g over L sin theta plus b over ml square theta dot equal tau naught over ml square cos theta. Applying small angle approximation, we get sin theta equals theta. And let's define some constants, omega naught as g over L lower under root, beta as b over 2 ml square. B over 2 ml square is beta from this figure, from this equation. And alpha naught is tau naught over ml square, this one. So putting values of theta, theta dot and theta double dot in the equation, we get terms containing omega square, omega naught square, minus 2 beta omega with amplitude at common on left side. On right side, it is just alpha naught cos omega t. So expanding formula cos omega t minus phi, these terms, and also sin omega t minus phi. This can be expanded as this term, as d2 term. So comparing coefficients of cos omega t and sin omega t on both sides of this equation, we get omega naught square minus omega square into cos phi plus 2 beta omega a sin phi equal alpha naught. There is no sin omega t terms on right side, plus 0 into sin omega t. So left hand side equal right hand side. This on simplification gives omega naught square minus omega square into tan phi minus 2 beta omega equals 0. This gives tan phi as 2 beta omega over omega naught square minus omega square. We can use tan phi relation to find sin phi and cos phi from this figure. And putting values of sin phi and cos phi back into previous equation, we are left with value of A, the amplitude of motion of the force driven pendulum, as whole square root omega naught square minus omega square whole square plus 2 beta omega whole square equal alpha naught, and this gives the value of the amplitude. Putting back value of the amplitude and the constant alpha naught, we get the value of steady state solution theta t as cos omega t alpha naught over 2 beta omega square plus omega naught square minus omega square whole square. We know the value of beta and omega naught as discussed earlier.